Consider 3 points on the corner of a triangle. We've got Q1 is equal to 6 nanocoulombs. Q2 is equal to -2 nanocoulombs. And Q3 is equal to 5 nanocoulombs. Find the resultant force on Q3. So we're going to find the resultant electric force on Q3 due to the electric forces from these other 3 charges, or from these other 2 charges. And our charges are separated on this triangle by the quantities I've listed here for each one of the legs. Okay, so in order to get this is a vector. Okay, this resultant force is a vector, so it's going to have a magnitude and it is going to have a direction. We're going to have to go through a lot of steps in order to get this force. So let's think about the strategic approach that we're going to use in order to figure out what F3 is going to be. Okay, so the first thing we have to think about is the direction of our forces. So we're going to draw those in. Then we're going to find the components of F23, which is the force that charge 2 exerts on charge 3. Then we're going to find the components of F13, that's the force that charge 1 exerts on charge 3. And then with that, we can find the magnitude and direction of F3. Okay, first, let's think about Q3 and the direction of the electric forces acting on it. So let's think about maybe the simplest one right here. We've got Q2 over here, Q3 over here. Q2 is negative, Q3 is positive. That's an attractive force. That means that the force that Q2 exerts on Q3 is going to be pulling them together. That force is going to be pointing toward Q2. So this is what I'm going to call F23. It's the force that charge 2 exerts on charge 3. What about the forces between Q1 and Q3? Well, Q1 and Q3 are both like charges. They're both positive. And the force between like charges is repulsive. They want to push each other away. So the force that Q1 exerts on Q3 wants to push Q3 up into this direction. So it's going to be along this same line right here between Q1 and Q3. That is the direction in which F13 is pointing, directly along this and opposite there. To get F, we're going to have to add F23 and F13. And of course, they're both vectors, so we have to break this up into the x and y component. So we could say that, let's see, F3x is equal to F13x plus F23x. F3y is equal to F13y plus F23y. And that will give us our components for the x and y component of F3. And from that, we can get the magnitude and direction of F3. Okay, so our first step is done. We figured out the direction that these forces between all of our charges are pointing, at least as they're acting on charge 3. And now we can start working on getting the components of F23. That'll be our next step. I chose to do that one next because it's a little bit simpler here. In order to get the magnitude of F23, we use our equation for the Coulomb force, the electric force between Q2 and Q3. So we've got our Coulomb constant times the absolute value of Q2 times the absolute value of Q3 divided by the distance between them squared. Okay, and so that's going to equal 8.99 times 10 to the 9 Newton meters squared over Coulomb squared times Q2 is 2 nanocoulombs. Nano is times 10 to the minus 9. So we've got 2 times 10 to the minus 9 coulomb. We've got our absolute value signs around the charge since we're just finding the magnitude of this force, so we drop the sign on the charge. And then Q3 is 5 nanocoulombs, 5 times 10 to the minus 9 coulombs. And we divide by the distance between them squared. The distance between charge 2 and charge 3 was 4 meters here on my diagram. So we divide by 4 meters squared. Then the magnitude of F23 is 5.62 times 10 to the minus 9 newtons. All right, and that's the magnitude of F23. Now, if we think about the components of F23, this is a little bit easier. F23 is only pointing in the x direction. It's in the negative x direction. So F23x is equal to minus 5.62 times 10 to the minus 9 newtons. F23y is actually just 0. There's no y component. So these are my components of my vector F23. That's the force that charge 2 is exerting on charge 3. Now, in between takes here, I decided actually to clear up our clutter here. It might be a little bit better to organize our thoughts if I place the components of my forces into a chart or a table. So here I've created kind of a table where I've got my 3 forces, F13, F23, and then F3, which is what we're trying to get to in the end. And I have columns here for the x component and the y component of those forces. So we just found the x and y component of F23. The x component was minus 5.62 times 10 to the minus 9 newtons. I've put that here. Our y component was 0 newtons. So we can fill in what we get for F13 here, and that will help us get F3 here in the end. So our next piece that we have to do here is figure out what is the force that charge 1 exerts on charge 3, the magnitude, and we'll get the components of that force. So in order to get the magnitude, we use, again, our equation for the magnitude of the Coulomb force. So this time we're thinking about F13. F13 is equal to our Coulomb constant times Q1 times Q3 over the distance between them squared. So again, we have 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. And then we multiply it by Q1, which was 6 nanocoulombs, 6 times 10 to the minus 9 coulombs, and times Q3, which was 5 nanocoulombs, 5 times 10 to the minus 9 coulombs. And we divide it by the distance between them squared. The distance between Q1 and Q3 is 5 meters. 5 meters squared. Okay, so the magnitude of this force is 1.08 times 10 to the minus, 10 to the minus 8 newtons. All right, that's the magnitude of F13. Okay, but it's not as simple as what we had for F23, because F13 has both an x and a y component. You see that F13 is pointing off, up, and to the right. So it has an x component. This is its x component, and it has a y component. This is its y component, and there's an angle in here. So we have to figure out how we can get the x component of F13 and the y component of F13, and we do that by thinking about geometry. Maybe what I'm going to do is I'm going to take this part of my drawing, I'm going to chunk it out, I'm going to move it, and I'm going to draw it over here. So we've got my third charge, and I had my force pointing this way for F23, and I've got my force pointing off in this direction for F13. Okay, And we have, okay, way down here is where my other charge is, Q1. This was Q3, okay? And so my vector F13 is going to have an x component right here. This is F13x. And it's going to have a y component right here. This is F13y. Okay, so in order to get these components, we've got a right angle triangle right here. The hypotenuse of this triangle is my magnitude of my vector F13, so that's what we just calculated. You can think about that as the hypotenuse of this triangle. In order to get F13x and F13y, we can use sine or cosine, but we also have to know this angle in here, this angle theta. I call that angle theta. Well, how do we get that angle theta? Well, this angle theta is the same as this angle theta right here, this angle theta. We call these vertical angles. They're called vertical angles because they share the same vertex. This is the vertex here. And so when we have these two lines intersecting like this line and this line are intersecting, these two angles are the vertical angles and they are equal to each other. Whatever we find for theta over here is the same as theta over here. To get this angle theta, we have to come back to our charge triangle. We've got a right angle right here. This is a right angle. We've got sides of 3, 4, 5. We know the sides. So to get our angle theta right here, just the same as this angle theta here, we can use sine, cosine, or tangent in any way in order to get, because we know all three of the sides, we could use sine, cosine, or tangent in order to get this angle right here. So it doesn't matter which we do. I'm going to use tangent to get this angle theta. So if I do that, where will I draw that? Maybe I'll do that over here. Tangent of this angle theta will equal to the opposite side of my triangle over the adjacent side of my triangle. For this angle theta, my opposite side is 3 meters. My adjacent side is 4 meters. So tangent of my angle theta is going to be opposite 3 meters over 4 meters. So tangent of theta is going to be 3 meters over 4 meters. And the meters cancel. And to get theta by itself, we have to take the inverse tangent of both sides. So theta is the inverse tangent of 3 over 4. And that gives us an angle of, we'll call that 37 degrees. Okay. This angle here is 37 degrees. To get F13y or F3x, using this angle, we've got our hypotenuse, we've got one angle of this right angle triangle, so we can use sine or cosine in order to get the components of this, this vector. Which leg will we start with? Let's just start with cosine and see where we go from there. Let's do cosine of this angle here. Cosine of theta equals adjacent over hypotenuse. So cosine of my angle theta is going to be F13x divided by the hypotenuse of my triangle, which is the magnitude of F13. So F13x equals the magnitude of F13 times cosine of my angle theta, cosine of 37 degrees. Okay? If I take 1.08 times 10 to the minus 8 newtons, right here, times cosine of my angle 37 degrees, then I get the magnitude of F13x, which is 8.7 6.3 times 10 to the minus 9 newtons. F13 is pointing up and to the right. Okay, so it has a positive x component. I can go ahead and put F13x up here in my chart, in my table. It's going to be positive 8.63 times 10 to the minus 9 newtons. Then for the y component of F13, we did cosine for the x component, so we can do sine for the y component. Sine theta equals F13y over the magnitude of F13. So F13y equals the magnitude of F13 sine of my angle theta, which is 37 degrees. So take 1.08 times 10 to the minus 8 newtons times sine 37 degrees, and that will give me 6.5 times 10 to the minus 9 newtons. And it also has this component is positive. The y component is upward for this vector F13. So over here in my table, I'm going to say for F13y positive 6.5 times 10 to the minus 9 newtons. Okay, now we've done all of the work in order to get the x and y components of F13 and F23. Now we can add them together in order to get the magnitude of F3 and the direction of F3. We are in the home stretch. We've done really most of the hard work in order to get to our final answer, which was trying to find our vector F3 here, the magnitude and the direction for the electric force acting on charge 3 because of the presence of charge 1 and charge 2. Now, we wrote down here that the x component of F3 is going to be the sum of F13x plus F23x, and then the y component of F3 is going to be the sum of F13 plus F23. Well, actually, we already have our chart arranged really nicely here for us. So what I'll do in order to get F3x is add F13x, 8.63 times 10 to the minus 9 newtons, and F23x, which is minus 5.62 times 10 to the minus 9 newtons. And whenever I do that, I get a value of positive 3.01 times 10 to the minus 9 newtons. And for y, the y component of F3y, we add F13y plus F23y to get F3. There's no y component for F23, so that's just positive 6.5 times 10 to the minus 9 newtons. So if I wrote F3 in unit vector notation, this would look like, well, we could write like this, F3x plus F3y. This is I hat, j hat. So the I hat means that we're in the x direction on our axis, and the j hat means we're in the y direction along our axis. Those are our unit vectors from last semester. And so that would equal 3.01 times 10 to the minus 9 newtons I hat plus, we're running out of room here, 6.5 times 10 to the minus 9 newtons j hat. Let's think about what that vector looks like. So if we have charge 3 right here, we have the x component, F3x, which is positive, and we've got the y component, F3y, which is positive, and then we have our vector F3, which is also positive in the x, positive in the y, so it's pointing up and off along this direction here. That's F3. Okay, so we found that component F3x, we found this component F3y. In order to get the magnitude of this vector right here, we can use the Pythagorean theorem. We can say that this side, our hypotenuse, is C. This side, the x leg, we can call A. This side, the y leg, we could call B. So remember, in our Pythagorean theorem, c squared is equal to a squared plus b squared. Then to get the magnitude of F3, we could take, so remember the magnitude, we can draw these little lines around it. The vertical lines means the magnitude, just the size, will equal to the square root of F3x squared plus F3y squared. Okay, so if I take F3x squared, 3.01 times 10 to the minus 9 newtons squared, plus F3y squared, 6.5 times 10 to the minus 9 newtons squared, and took the square root of that whole thing, I will find that the magnitude of F3 is 7.16 times 10 to the minus 9 newtons. So that's the magnitude. That's the size of F3. But this does not tell me the direction for F3. To get the direction for F3, we usually report our directions in angles, angles from the positive x-axis. So in order to get that, I've got my triangle here. I've got my x component. I know my y component. Here's my angle theta. This is my angle that my vector is sitting with respect to the positive x-axis. So I'm going to find this angle theta. And I can find that angle theta by using tangent. So tangent of my angle theta is equal to opposite side, which is F3y, over the adjacent side, which is F3x. So my angle theta is the inverse tangent of F3y over F3x. So if I take the inverse tangent of F3y, so 6.5 times 10 to the minus 9 newtons, and divide it by F3x, 3.01 times 10 to the minus 9 newtons, that will give me this angle here. And that angle is 65.1 degrees. Okay, so my magnitude of F3 is 7.16 times 10 to the minus 9 newtons at an angle of 65.1 degrees. Let's see where this vector lives in relationship to F23 and F13. So over here, we took this part of my drawing and blew it up over here. F23 is pointing off in this direction. That's the force that charge 2 exerts on charge 3. F13 is pointing off in this direction. That's the charge that Q1 exerts on Q3. We had to add both of these vectors together in order to get the net force that's acting on this charge right here. And that net force is this one that I'm going to draw right here. That net force is at an angle of 65.1 degrees. I didn't quite draw that correctly there. 65.1 degrees away from the positive x-axis. And it has a magnitude of 7.16 times 10 to the minus 9 newtons. So here is where my vector F3, the net force acting on charge 3, lives. Okay? So the purpose of this problem is to show you that electric forces are vectors. We needed to practice vectors because we haven't done that since first semester. A lot of work in order to get to this final answer right here. This is definitely something that I wouldn't be asking you to do on an exam, for example, but I will be asking you to do it in a workbook problem.